Cell 1. In this cell, we delve into the intricacies of genetic algorithms and simulated annealing, uncovering their relevance in the analysis of portfolio systems. Rather than simply optimizing numbers, these methodologies allow us to explore the underlying structures and dynamics that inform how capital is allocated within a portfolio. This broader perspective shifts the focus from mere statistics to understanding the relationships and behaviors that drive financial outcomes. We start by contrasting traditional portfolio optimization, which often views a portfolio merely as a vector defined by weights influenced by mean returns and covariances, with our innovative approach that treats a portfolio as a dynamic decision-making process. This process evolves over time, constrained by factors such as policies, costs, and behavioral considerations. It becomes clear that looking solely at weight distributions doesn't provide the full picture. Two assets might hold the same weight, yet can carry significantly different implications for risk and return. Clustering emerges as a powerful tool in this context, highlighting the structural relationships among assets rather than merely ranking them based on Sharpe ratios or weights. It enables us to identify groups of assets that behave similarly, shedding light on redundant exposures, potential diversifiers, and concentrated risk pockets within our portfolio. The advantage of this method lies in its improved interpretability. Instead of simply reporting the output from an optimizer, we can articulate that our portfolio is composed of distinct allocation clusters, such as high-return core assets, medium-risk diversifiers, and low-weight satellites that aim to reduce overall correlation. Moreover, this analytical framework allows us to separate asset selection from the allocation process, giving valuable insights into market structure. By examining which clusters attract capital, we can diagnose potential issues like overconcentration or unintended bets, as well as assess sensitivity to different market regimes. This capability enriches our understanding of not just what weights we have, but also why they might change over time. To enhance our analysis further, we can employ repeated examinations across different timeframes, rolling windows, and multiple optimizer runs. This will allow us to assess cluster persistence, the stability of weights as they shift between clusters, and whether our allocations demonstrate consistency or volatility. However, it's crucial to remain aware of the potential pitfalls. Clustering can sometimes create misleading narratives, as clusters may emerge even amidst random noise. The results we derive heavily depend on the choice of features. For instance, the clustering approach could be influenced by different variables, such as returns and volatility, weights and risk contributions, or correlations through principal component analysis, each leading to divergent cluster formations. Additionally, we need to consider the inherent limitations of methods like k-means, which assumes spherical clusters, similar variances, and relies on Euclidean geometry. As we move forward, the next cell will likely build upon this groundwork, exploring how to effectively implement these concepts in practical applications and diving deeper into the specific methodologies used to understand and govern portfolio behavior. Cell 2. In this cell, we are diving into some essential financial analytics involving price and return calculations, which are crucial for understanding asset performance. The code sets up several functions that will allow us to compute returns from price data, assess portfolio characteristics, and optimize investments based on the Sharpe ratio, a critical measure of risk-adjusted return. The first function, prices to returns, handles converting price data into percentage returns. By sorting the index and using the percentage change method, it creates a new data frame of returns while dropping any NaN values that might arise from the calculation. This ensures that we work with clean, reliable data as we proceed. Next, we encounter the portfolio stats function, which takes returns and weights to calculate crucial portfolio metrics like expected return, volatility, and the Sharpe ratio. It does this by first determining the average return and the covariance matrix from the returns data frame, scaling these values to an annual basis using a preset factor. This is vital because it allows for a clearer comparison across different time frames. The weight vector is then used to compute the portfolio's expected return and its volatility, with special care taken to handle the scenario where volatility is negligible, preventing division by zero. Moving on, we examine the objective neg-sharp function, designed to minimize the negative Sharpe ratio, incorporating a turnover penalty when changing weights. This means that not only are we aiming to maximize our risk-adjusted return, but we're also considering the cost of trading by evaluating how much the weights shift from their previous values. This dual focus ensures that our strategy is not just effective in theory, but also practical in implementation. Lastly, the project to simplex long-only function helps to ensure that our portfolio weights remain practical. They can't be negative and should sum to 1. By clipping and renormalizing the weights, the function enforces these constraints in a straightforward manner. As we proceed to the next cell, we'll likely explore how to apply these functions to real-world data, leveraging the capabilities we've just built. This will lead us into the realm of practical investment strategies, providing a solid foundation to make informed decisions guided by the metrics we've calculated. Cell 3. In this cell, we're implementing a genetic algorithm to optimize a portfolio's asset weights, which is crucial for maximizing investment returns while managing risks. This method blends principles from biology with computational techniques, allowing us to evolve potential solutions over multiple generations. The function starts by defining key parameters, such as the population size and the number of generations. Importantly, we also have control mechanisms for elite retention, tournament selection, mutation, and crossover, which are fundamental to genetic algorithms. Using a random number generator seeded for reproducibility, we generate an initial population of asset weightings that lie within a defined space using a Dirichlet distribution. This ensures that all weights sum up to 1 and are non-negative, which is vital for long-only portfolios. The fitness of each portfolio is then evaluated using a negative Sharpe ratio. The choice to maximize this measure means we want portfolios that not only yield high returns, but do so with relatively lower volatility. The tournament selection process allows us to choose the best performing portfolios for reproduction, ensuring that stronger candidates have a higher chance of passing on their genes to the next generation. Crossover combines the features of parent portfolios to explore new potential solutions, while the mutation process adds genetic diversity, helping us escape local optima. Throughout generations, we continuously evaluate the best performing portfolios, keeping track of the one that yields the highest fitness score. After all generations are executed, the function returns the optimal portfolio weights, along with their corresponding fitness score. It's important to be aware that while this approach is powerful, it can sometimes converge prematurely or get trapped in local maxima if parameters are not carefully tuned. In the next cell, we'll likely explore how to analyze the resulting portfolio's performance metrics and possibly compare it against benchmarks, providing further insight into its effectiveness in real-world investment scenarios. Cell 4. In this cell, we're implementing a simulated annealing approach to optimize a portfolio's weights based on historical returns. This technique is valuable because it allows us to escape local optima that simpler methods may get stuck in, ensuring more robust portfolio performance. The function starts with a few critical parameters: the returns data, the number of optimization steps, the initial and final temperatures, and a scaling factor for the weight adjustments. The random seed ensures reproducibility, which is crucial for consistent portfolio evaluations. An initial equal weight distribution is established, ensuring that the portfolio starts balanced across the assets involved. To bring this balance into compliance with our restrictions, we project these initial weights into the feasible space using a helper function. That's where we ensure the weights make sense, considering the constraints. Next, we define an energy function that assesses the current portfolio's performance using the negative Sharpe ratio, which is a measure of risk-adjusted return. This function will guide our search for better solutions as we navigate through the weight space. The optimization works by using an exponential cooling schedule, allowing our algorithm to gradually reduce its temperature. This reflects the decreasing likelihood of making radical changes as we progress through optimization steps. During each of these steps, we propose changes by randomly selecting two assets and transferring a small portion of weight from one to the other. This is where the step scale comes into play, as it dictates how much weight can be shifted. However, we must ensure we don't violate any constraints, leading us to adjust our new weights accordingly. The core of this process is the Metropolis acceptance criterion, which decides whether we should keep the new weights or revert to the current ones. If the new portfolio delivers a better performance, or if it offers a reasonably good trade-off, even when it's worse, we proceed with the new weights. Throughout the iterations, we keep track of the best performing weight configuration encountered. By the end of this function, we return the weights that produce the highest expected Sharpe ratio, allowing future decisions on asset allocation to be based on well-optimized criteria. In the upcoming cell, we're likely going to visualize these results or perhaps analyze how different parameter settings could influence our portfolio's performance. Cell 5. In this code cell, we're setting the stage for a financial data analysis by leveraging the Y-Finance library to fetch stock prices for a curated selection of ticker symbols. This matters because accessing up-to-date stock information is essential for any financial modeling, investment analysis, or market trends exploration. First, we import the necessary libraries: Y-Finance for downloading the stock data, Pandas for data manipulation, and NumPy for numerical operations. Next, we define a list of tickers representing major companies across various sectors. These include tech giants like Nvidia and Apple, retail leaders such as Amazon and Walmart, and financial heavyweights like JP Morgan Chase. Each of these tickers is a symbol that corresponds to a specific publicly traded company, and analyzing them together allows us to grasp broader market dynamics. We also establish two key variables to define the time frame we're interested in. The start date is set to January 1st, 2025, while the end date is left as none, which instructs the code to fetch data available up to the most recent date. This flexibility allows us to always have the freshest insights without needing to update the end date frequently. As we move forward, it's important to remain aware of potential pitfalls. For instance, the absence of data after the start date could impact our analysis if stock prices don't become available or if there's an issue with fetching data from the source. In the next cell, we will likely proceed to actually pull this data into a data frame, setting the groundwork for further analysis or visualization. This will enable us to examine trends, make comparisons, or even conduct more sophisticated financial modeling based on the rates of return or other metrics derived from the data we collect. Cell 6. In this code cell, we're pulling historical stock data using the Yahoo Finance API, which is a crucial step for any analysis involving financial time series. The focus here is on obtaining daily closing prices for a set of ticker symbols over a defined date range, making sure the data is automatically adjusted for any stock splits or dividends, which can significantly affect analysis outcomes. First, we initiate a download of data by specifying the tickers we want, along with the start and end dates for our dataset. The interval is set to daily, which allows us to analyze the data on a day-to-day basis. A key point here is that we use the auto-adjust parameter, which ensures that the closing prices we receive are adjusted for any corporate actions, enhancing accuracy in our analysis. Once we have the raw data, we focus on the close prices, dropping any entries that don't have values for all tickers. It's essential to clean the data like this because any missing values can skew our analysis. After that, we sort the index to maintain chronological order, which is a crucial aspect when dealing with time series data, since chronological order affects our calculations and interpretations. Next, we convert the cleaned closing prices into returns, which is vital for understanding performance over time. Returns give us insights into how much the investment would have gained or lost, rather than just looking at price levels. Finally, we display the first few entries of both the prices and returns datasets, providing a snapshot of the data to validate our approach. As we move to the next cell, we'll likely delve deeper into analyzing these returns, perhaps calculating various metrics or visualizations that will further illustrate the trends and patterns in the stock data. This preparatory step sets a strong foundation for the forthcoming analysis. Cell 7. In this code cell, we're developing a complex month-end portfolio optimization strategy that accounts for market realities, such as transaction costs and risk controls. This is crucial for making informed decisions about asset allocation at the end of each month, while balancing the need for performance with practical considerations. The logic kicks off with the retrieval of historical price data using the Y-Finance library. This data is then processed to derive returns, enabling us to assess how investments are performing over time. From there, we implement constraints on our portfolio to ensure it adheres to specific investment rules. For example, we define a maximum weight for any single asset and allow only a specified number of top assets to influence our portfolio, promoting diversification while adhering to risk management practices. As we progress through this workflow, we compute transaction costs associated with rebalancing, ensuring that the defined constraints around weight and turnover are respected. The project portfolio function plays a vital role here, taking raw weights and adjusting them to meet our strategic criteria, which facilitates a disciplined approach to investing. The objective function we devise is finely tuned to maximize the Sharpe ratio while minimizing penalties for turnover and transaction costs. This dual focus ensures we're not only pursuing high returns, but are doing so efficiently. We utilize both genetic algorithms and simulated annealing as optimization techniques, demonstrating a flexible approach to evolving investment strategies. Each method seeks to improve the portfolio allocation by finding the optimal weights that navigate the outlined constraints. It's informative to note that the program factors in parental weights from previous allocations, emphasizing a strategy rooted in historical performance while mitigating sudden changes that could disrupt the portfolio. This careful balancing act is essential for maintaining stability in investment outcomes. As we move to the next code cell, we'll likely delve deeper into implementing and analyzing the outcomes of these optimization techniques, further refining our approach to achieve meaningful results in real-world portfolio management. Through this upcoming exploration, it'll be exciting to see how our theoretical framework translates into practical applications. Cell 8. In this cell, we're diving deeper into the analysis of investment returns by calculating key metrics that will help us understand the performance of different assets within a portfolio. Specifically, we're focusing on expected returns, volatility, and contributions to risk and return for each security. These calculations are essential for effective portfolio management, since they provide insights into how well different assets are performing relative to the risk they carry. To start, we calculate the mean and standard deviation of the asset returns, annualizing these metrics based on the typical number of trading days in a year, which is 252. By multiplying the mean returns by this annualization factor, we derive the expected returns for each asset. Similarly, we annualize the volatility, which is crucial for understanding the risk involved in each investment. Next, we define which set of weights to visualize, depending on whether we've used a genetic algorithm in earlier computations or a final weight set. This flexibility allows us to adapt our analysis based on the optimization method employed earlier in our analysis. We then create a data frame to hold our data, including tickers, expected returns, volatilities, and selected weights. This structured approach allows for clear and efficient manipulation of our metrics as we dive deeper into the analysis. In the following calculations, we introduce additional metrics to enrich our understanding. For instance, the weighted expected return contribution provides insight into how much each asset contributes to the overall return given its weight in the portfolio. The marginal risk contribution is computed using the covariance matrix of returns. helping us assess how much risk each asset adds to the portfolio based on its current weights. If the portfolio volatility is non-zero, we calculate both the marginal risk contribution and the overall risk contribution for each asset. This is crucial because it allows us to identify which assets are providing more risk in the portfolio relative to their expected returns. Finally, we also compute the standalone Sharpe ratio for each security, which serves as a measure of risk-adjusted return. After handling any potential infinite or undefined values, we sort the data frame by weights to highlight the top assets in the portfolio based on their significance. Looking ahead, the next cell will likely leverage these insights to guide potential adjustments in portfolio allocation or further refine our analysis of performance metrics on different securities. This continuous examination is vital for making informed investment decisions. Cell 9. In this code cell, we're harnessing the power of Plotly Express to create an insightful scatter plot that visually represents the relationship between risk and return for different investments. This visualization is crucial as it not only highlights individual asset performance, but also provides a clear understanding of how portfolio weights impact both expected return and volatility. The primary focus here is on the scatter plot, where we're mapping annualized volatility on the x-axis against the annualized expected return on the y-axis. Each point in this plot represents a different asset, and what's particularly interesting is how the size of each bubble corresponds to the weight of the asset in the portfolio. A larger bubble indicates a more substantial investment in that particular asset, allowing us to intuitively grasp the impact of varying investment levels. As we dive into the hover data, we see more detailed metrics available at our fingertips. When we hover over a bubble, it reveals not just the ticker symbol, but also several critical financial metrics, such as the weight, expected return as a percentage, volatility percentage, along with risk and return contributions. This additional context enhances our understanding as we examine the trade-offs between risk and reward. It's important to consider the assumptions inherent in our analysis. For example, we're presuming that our dataset, represented by the variable dfsec, contains accurate and relevant information regarding these financial assets. Any errors or discrepancies within this dataset could lead to misleading conclusions. Additionally, while the scatter plot effectively illustrates our point, viewers should remain cautious as this type of visualization does not account for the correlation between different assets, which could significantly affect portfolio risk. Looking ahead, in the next cell, we will likely expand on this visualization by introducing further analytical aspects, perhaps exploring optimal asset allocations or examining specific risk-return profiles in greater detail. This would enhance our investment strategies, leveraging the insights gained from the current plot. Cell 10. In this cell, we're diving into a clustering analysis of the investments in our portfolio, specifically focusing on those assets that we actively hold. By clustering these positions, we can gain insightful distinctions based on their weight, risk contribution, and return contribution, which can inform our overall investment strategy. To start, we filter our dataset to keep only the securities that have a positive weight, meaning these are the assets we're actually invested in. We then extract relevant features from this subset, including their weight, risk contribution, and return contribution. To prepare this data for clustering, we standardize it using the standard scaler. This ensures that all features contribute equally to the analysis, which is crucial because otherwise, variables with larger ranges could unfairly influence the outcome. Next, we determine the number of clusters. We set a maximum of 4, but we also ensure it's adaptable if the number of held positions is smaller, as we wouldn't want to attempt clustering more groups than we have data points for. Using k-means, We then fit our defined clusters, effectively categorizing our held positions based on their attributes. And we assign each position to a specific cluster that reflects its characteristics. Once that clustering is complete, we visualize the results using a scatter plot. Here, the x-axis represents annualized volatility, while the y-axis shows annualized expected return. The points are color-coded by cluster, with each asset's size representing its weight in the portfolio, making it easy to identify not only how clusters relate to each other, but also the relative importance of each asset within those clusters. It's worth noting that this analysis operates under the assumption that our dataset is well prepared, with no missing or inconsistent data. If issues exist in our data, they could significantly affect clustering outcomes. As we look to the next cell, we're likely to delve deeper into these clusters, exploring their implications for our investment strategy and how we might optimize our portfolio further based on these insights. Cell 11. In this cell, we're diving into the process of clustering all the securities based on a variety of features, while incorporating weight as a key component. This is crucial because it allows us to identify distinct groups of securities that share similar characteristics, which can inform investment decisions. We begin by selecting a few important features from our securities dataset: weight, expected return, volatility, and the standalone Sharpe ratio. These features give us a comprehensive view of each security's performance, and by standardizing these values, we set a common scale. This standardization is essential to ensure that no single feature disproportionately influences the clustering result. Next, we define the number of clusters we want to create, which in this case is set to 5. We then initialize the k-means algorithm with multiple random initializations to increase the chances of finding a stable solution. After this setup, we apply the k-means clustering, which assigns each security to one of our predefined clusters. One important consideration we address is ensuring that weights of 0 do not lead to invisible points on our scatter plot. To tackle this, a small epsilon value is introduced, ensuring that even those securities with a minimal weight are represented visually, which is crucial for our analysis. As we create a scatter plot, the x-axis represents annualized volatility, while the y-axis shows annualized expected return. This visual representation helps in assessing the trade-off between risk and return for each cluster. The bubbles in the plot are sized according to the security's weights, which means that larger bubbles indicate a higher allocation in the portfolio. Through this analysis, we gain insights into which clusters may offer attractive risk-return profiles. This information is vital for strategizing future investment allocations and understanding security dynamics within each cluster. Looking ahead, the next cell is likely to explore these clusters in even greater detail, perhaps by evaluating the performance metrics associated with each group, or examining how these clusters evolve over time. This could provide valuable context for making informed strategic decisions in our portfolio management. Cell 12. In this cell, we're diving into the concept of gradients and why they're not applicable in certain scenarios, particularly in the context of our optimization problem. Understanding this is crucial, as gradients are typically fundamental to many mathematical and machine learning techniques that rely on smooth optimization landscapes. The discussion opens by highlighting specific assumptions necessary for gradients to exist. First, we consider continuity, which means that small changes in input should result in small changes in output. If this condition isn't met, we could encounter sudden jumps in our results, making it impossible to define a clear gradient. Next is differentiability, where the function must be smooth enough to have a defined derivative at every point of interest. If there are discontinuities or sharp transitions, we run into similar issues. We also touch on convexity, or its near relative, which signifies that the function has a single global minimum that's easy to identify. If the function lacks this property, we could be misled by local minima, preventing effective optimization. Additionally, factors such as maximum weight caps and turnover penalties complicate the landscape further. These constraints can introduce nonlinearities and discontinuities that disrupt the smooth transitions needed for gradient-based methods. Another important aspect mentioned is the strategy of rebalancing only when a certain drift exceeds a defined threshold. While this approach can serve to manage risk, it introduces another layer of complexity that fails to align with gradient assumptions, potentially leading to erratic results if not handled carefully. In essence, this discussion sets the stage for the challenges one might face when working with optimization in non-ideal scenarios, drawing attention to the need for alternative methods. As we progress to the next cell, we will likely explore strategies that bypass these gradient limitations, offering a fresh perspective on how we can tackle optimization when traditional methods aren't viable. Cell 13. In this closing cell, we're wrapping up our exploration of the entire Jupyter Notebook, which is essential because it helps us summarize the insights we've gained and solidify our understanding of the material we've covered. This step not only provides a sense of closure, but also emphasizes the journey we undertook through the various analyses and visualizations. As we conclude, it's beneficial to reflect on how the different components we explored all fit together. Throughout the notebook, we examined distinct datasets, applied various methodologies, and generated visual representations that deepened our insights into the underlying phenomena. Each step was designed with a purpose, addressing specific questions that arose from our analysis. It's crucial to note how these components, like the data preparation, the exploratory analyses, and the final visualizations, play a cohesive role in building our understanding of the topic at hand. By consolidating our findings, we can better appreciate the key takeaways. This not only reinforces what we have learned, but also prepares us for further investigation. As we transition to the next part of our learning, we should consider how the insights gathered here can inform future projects or analyses. The groundwork we've laid will undoubtedly prove beneficial as we dive into more advanced concepts, expanding our toolkit and analytical capabilities even further. In the upcoming sections, we will build upon the knowledge from this notebook, exploring how to apply these insights to more complex scenarios and possibly introducing new methodologies for innovative problem solving. This leads us into an exciting phase of discovery, where we once again engage with the data in fresh and intriguing ways.